Hi everyone, welcome to my new channel, which is all about algebra, arithmetic, and more. By the name, you can tell that this can be a math channel, and I'm going to be posting different math concepts and videos explaining these concepts with perhaps maybe some practice questions as well. And a big reason why I started this is because I found myself interested in math, and I'm currently a university student studying in a math-focused major, computer science. So I figured why not help other people with the knowledge that I have. I've been tutoring, and my friends have also come to me for help. So I decided to come up with, uh, decided to kind of market myself to a larger audience than restricting myself to the people around me. And what better way to do it than through YouTube? So um, that's a little kind of insight as to why I chose to do this, and I'm going to talk a little bit about what I'm starting with. I'm actually starting with an introduction to proofs. I'm going to be talking about how to do proofs, like mathematical proofs, and go through that because mainly because I was actually working through proofs. This is my first proofs course in university, and I really enjoyed the content that it taught. And I felt like it's a category of mathematics, like it's a topic in mathematics that is very confusing to wrap your head around because you don't really learn about these techniques until much later in your career, like much later in your education. So I think this was like a good place to start, especially considering that a lot of students tend to struggle on this and find it a little bit difficult. So in today's class or video, I should say, we're going to be discussing kind of like an introduction to proofs, introduction to the language of mathematics. So what is proofs? Proofs is a way, I'm going to do this in a different color actually, way to prove a mathematical statement. So proofs are simply just a way to prove a mathematical statement. Well, what does this mean? What is a mathematical statement, right? What is this? We don't know what that is, right? We don't, because we haven't looked at anything. But tell you what, we have looked at these statements before. You've Once you see the format of what a mathematical statement is, you will understand um, that it'll seem familiar. It'll be concepts that you've learned before, and you'll understand that this is something I've looked at before, but never paid too much attention to it. And now it's going to be your sole focus for this course, or for proofs, solving proofs, proving proofs actually. Um, well, what is a proof? Well, a proof consists of, so proofs consist of the following. There's a couple parts to a proof. So there's language, right? How you communicate, your proof, right? There is precision. How precise are you with your proof? And we'll get into what that means later. And then there is notation, so how you write your proof, right? This could be maybe symbols, numbers, right? Etc. Right? Because symbols and numbers, these all kind of as notation, because as you're going to move forward, you're going to learn notation. And finally, logic and argumentation. And what is this? This is like reasoning. Does it make sense? Right? For example, if I said 2 is equal to 1. I mean, does that make sense logically? No, because they're two independent numbers. 1 is its own number and 2 is its own number. They're not equal to each other, so that logically does not make sense, right? I can't say 1 is equal to 2 because logically does not make sense, right? So logically saying 1 is equal to 2, it just doesn't make sense, right? Now, here are some questions to consider when you're solving proofs. So some questions you want to ask yourself when you're solving proofs are, well, is it true? Is it false? Right? Because you want to ask yourself, is this statement true? Is what is being said true or is it false? And if so, can you convince me? So it's like saying, 1 is equal to 2. Well, that is false, but what is your reasoning? Or you could argue that it's true, but what is your reasoning for that? And you would have to provide a proof as to why you think 1 is equal to 2, because you can't just say, I think this, that's why it's this. You would have to say, I think this, and this is the evidence to back it up. I have proved that that this is true, right? Now here's an example. Now let's take a look at mathematical statements, and then I'll show you a couple examples of what uh, a mathematical statement exactly is. So a mathematical statement consists of different parts. Okay, so there can be different parts of a mathematical statement. So this is an example of what a mathematical statement looks like. So here's an example of what a mathematical statement would look like. So this is an example of a mathematical statement. For every positive integer n squared plus 1 is not a perfect square, right? So what they're trying to say here is that they gave you a restriction, kind of like they gave you this variable. So they're saying, we know that n, right, is some variable. It's a positive integer, right? It's a positive integer such that n squared plus 1, this part, is not this. And of course, you could, obvious way, the obvious way to solve this would just be plug values that are positive integers, right? And check. And of course this would work, but here, this is an important part, right here. This right here, for every. Now, if it said that, find, if it said, find a positive integer, then you could use guess and check, right? Which is what we would do if we plugged in values, right? Plug values that are positive integers and check whether it meets the requirement, right? But it says for every positive integer, which means that every single positive integer that exists, that means that this right here, this is true for every positive integer. So every single positive integer that exists, this will hold. Now, how can we prove this though, right? Like you can continuously check by plugging it in, but there are infinite positive integers. So how would you be able to show that this is true and holds for every single positive integer? And that is where we use proofs. So we use proofs to solve a mathematical statement. Okay, so I'm going to show you the format for a mathematical statement. So how is a mathematical statement formatted, right? Well, there would usually be something called a quantifier, right? Then we would have a domain. Then there's also a variable, an open sentence, and voila. Here, these 4 components right here are what a mathematical statement. Before we try an example, I'm going to talk about what types of mathematical statements there are. So now there's going to be types. Well, firstly, we have universally quantified, right? Which means that they are, because we know that, there's quantifiers, but then these break down. These break down into 2 types, right? So there's universally quantified, so all elements, right? Or for all, or for every. These are all ways of denoting this. So if we look back to this example right here, that we had right here, right there, we know that for every, right? So that means that we know that it's universally quantified because we're saying for every single value of n, this is satisfied, right? So that means that's universally quantified. Now, what if we wanted to say that it's not for all, but at least for one, right? Then that's existentially quantified, right? And this would mean there exists, or at least one, right? This means that, it's not true for all positive integers, but there can be one solution for the positive integer such that this is true. So if this said there exists positive integer n, such that n squared plus 1 is not a perfect square, that would mean that there's a possible value for n such that it would not be it would be a perfect square. And these can be denoted using symbols. So for this one, you'd use for all, it would look like an upside down A, and for the existential, you'd use a backwards E. We can make these a different color. Let's go with this color. Right. So, oops. Okay. So far, what we've discussed is we've discussed what a proof is. We've discussed what it consists of. We've discussed some questions to consider. We've also discussed what mathematical statements are and the components. And so far, we've discussed what a quantifier is, which means if you see this symbol, then that means it's saying, oops. If you see this symbol, then that means that it's saying either all elements or for all or for every. So you're trying to prove that for every single element given in the domain it's going to hold for this, right? And if you see this one, then it's saying that there is at least one. There is at least one solution. Now let's talk about domains. And these are going to be things that you've already seen before. For example, there's integers, right? There's real numbers, there is rational, there is natural, and I believe that's all we can discuss for now. Yeah, these four are the big ones that you're going to see. So what are integers? This is any whole number, right? So could be negative or positive. Could be positive or negative, doesn't matter. Or zero. They're all integers. Real number is any number. Really just any number, other than some exceptions. Other than, say, I, which is equal to the square root of -1, and etc. So like numbers that we cannot compute. So numbers that are computable. So numbers that are computable are called real numbers. Rational number is any number that can be written as a fraction. Right? Now, what would not be? So pi is not a rational number because pi cannot be represented as, a fraction. Now, natural numbers, it's similar to integers. These are kind of similar, except natural number is any integer greater than 1, greater than or equal to 1. In some contexts, they'll say that 0 is also a natural number, but usually in mathematics, we don't consider 0 as a natural number. We consider natural numbers, think of it this way, as counting numbers. You never start counting at 0, you always start at 1. So you do 1, 2, 3, 4, so it starts at 1 and it goes up by increments of 1. And then your variable would be your variable, which you're using here, right? In this case, it would be n, and your open sentence would be this part. So now let's break it down. So now if I have this statement, for every positive integer n squared plus 1 is not a perfect square. Right, so if I have this, right? Well, I know for all, right? So I know this part. So for every or for all, so that means that we know that's universally quantified, and we know that it's positive integers. And the natural numbers can be considered positive integers. But that's not the only way to write it symbolically. So we know that this would technically be the natural numbers. And we know that the variable is n. So this is our variable. And whatever's left, because it uses the variable and it's basically what we're trying to prove, is the open sentence. Right? So we've broken it down into all of its parts. And now if I were to change this equation to say there exists a negative integer n such that n squared plus 1 is not a perfect square, right? So we just took that and we changed a couple of things about it. Then we would say there exists, right? So that means that this is existentially quantified, right? We know that this would mean that it's negative integers, right? And we know that this is our variable again, and this is our open sentence. Open sent, and this is our variable. Okay, so now using this, now we can try to put it like a symbolic representation, right? Well, we know our symbols for all and existentially quantified. We can say that our integers are represented by capital Z, like that. Our real numbers are represented by this, and you might have seen this notation from other courses or somewhere else. We can represent our rational numbers by a Q, right, like that. And we can represent our natural numbers as an N, like that, right? So now let's take our two examples and try to convert them into symbolic representations. Oops. Okay, good. So now we know that these symbols, right? And we know from prior knowledge that if a variable is an element of a domain, we use this symbol. It's called epsilon. We use that, right? So let's put it together. Well, for every, right? We're gonna tackle this one first. So we know that for every positive integer, right? So we know that for every, because we use this symbol from before, positive integer n. So we know for every n, that's an element of the positive integers. Another way you could write this is z with the superscript plus, right? We know that this, comma, and then we can put our open sentence. So n squared plus 1 is not an open sentence. I mean, is not perfect square. My bad. And the same thing applies here. Right, so now we have figured out as to how to convert these into symbolic representations. Well, I'm going to give you guys about maybe 5 seconds. You guys can pause the video here and try to convert this into a symbolic representation and see whether you got it right. Okay, so now let's take a look at that one. Well, we know that there exists. We know our symbol from over here. It might be a little bit hard to see, so I can get rid of this and this. So we know that there exists, right? So there exists this, right? And we know that our variable is still n, so there exists n, which is an element of the negative integers, right? There's not really a symbolic way, like its own letter for the negative integers, so we can just put it as a superscript to the power negative. So always keep that in mind. If it's negative integers, you put it as a superscript negative. And then our open sentence is the same, so we put n squared plus 1 is not a perfect square. All right, so we've discussed on how to convert this into symbolic representations and this into symbolic representations. So in today's class, we went over what a proof is, the parts of a proof, questions to consider when you're solving a proof, mathematical statements, parts of mathematical statements, and how to write them symbolically. I believe that's all for today. Next class, we can dive a little bit deeper into like more of the logical and theoretical side of proofs,